Bismillahirrahmanirrahim. Good evening, my friends. In the last lesson, we talked about the AC synchronous generators and its main parts and construction of the synchronous generators. Today we gonna explain how does three-phase AC synchronous generators works. Now, the rotating and stationary parts of an electrical machine can be called as rotors and stators, respectively. The rotor or stator of electrical machines acts as a power-producing component and is called as an armature. The electromagnetics or permanent magnetics mounted on the stator or rotor are used to provide magnetic field of an electrical machine. The generator in which permanent magnet is used instead of coil to provide excitation field is timed as permanent magnetic synchronous generators, also simply called as synchronous generators. In general, synchronous generators consist of two parts, rotor and stator. The rotor part consists of field poles and stator parts consist of armature conductors. The rotation of field poles in the presence of armature conductors induces an alternating voltage, which results in the electrical power generation, as shown in these pictures. The rotor that consists of field winding, and the stator has armature winding. In the negative terminal, as shown, for each phase is 180 degrees from the corresponding positive terminal. Synchronous generator working principle. The principle of operation of synchronous generators is an electromagnetic induction. If there exists a relative motion between the flux and conductors, then an EMF or electromagnetic field is induced in a conductors. To understand the synchronous generator working principle, let us consider two opposite magnetic poles, as shown in this picture. It's north and this pole is called south. Two opposite poles. After completing 80 degrees rotation, the conductor's size A, B, the conductor size A and P, as shown in the picture, and C, then D, as shown, comes in the front of the S poles or south poles and N poles respectively. Thus, now we can say that the conductor tangential motion is perpendicular to magnetic flux lines from north to south pole. So, there introduced a flux or the magnetic flux between the N and S poles because the rotation of the N into 90 degrees. So here, rate of flux cutting by the conductors that's shown in this picture. The magnetic field cuts the conductors is a maximum and induced current in the conductor. The direction of induced current can be determined using the Fleming's right-hand rule. Thus, we can say that current will pass from A into B. The current is go from A into B and from C into D. If the conductor is rotated in a clockwise direction for another 90 degrees, then it will come to a vertical position as shown in the below figure. Now, the position of the conductors and magnetic flux lines are parallel to each other, and thus no flux is cutting and no current will be induced in the conductor. Then, while the conductor rotates from clockwise from or for such that the conductors AB and CD are under the N poles and S poles respectively. By applying Fleming's right-hand rule, current induced in conductor AB from the point B into A and current induced in a conductor C and D from point D into C. So, the direction of the current can be indicated as A, D, C, B, and direction of current of the previous horizontal position of rectangular turn is A, B, C, D. Is a 4 rotations. If the turn is again rotated towards a vertical position, then the induced current agent reduces to 0. Thus, for one complete revolution of rectangular turn, the current in the conductor reaches to maximum and reduces to 0, and then in the opposite direction it reaches to the maximum and again reach into 0. Hence, one complete revolutions of the poles north and south of the rectangular turn produces one full sine wave of current induced in the conductor, which can be termed as the generation of alternating current by rotating turn inside the magnetic field of the rotor. Now, if we consider a particle or a practical synchronous generator, then field magnets rotate between the stationary armature conductors. The synchronous generator's rotor and shaft or turbine blades are mechanically coupled to each other and rotate at synchronous speed. Thus, the magnetic flux cutting produces an induced EMF or electromagnetic field, which causes the current flow in armature conductors. Thus, for each winding of the stators, the magnetic flux coupled for each winding, the current flows in one direction for the first half cycle and current flows in the other direction for the second half cycles. And to lag of 120 degrees as they displayed by 120 degrees. Hence the output power of this code, it's called the synchronous generators power. Then the speed of the synchronous generators, it's abbreviated by this law. The speed of field pulse is synchronous speed is given by this law. That's called NS equals 120 F over P. What does mean? The NS, it's the abbreviation of synchronous speed. The synchronous speed of the generator's pulse, it's called NS, equals 120 F. 120, it's the rotate the phase or the ball in from the A into B, then into C. It's measured 120 degrees. Then it's multiplied by the F. F is abbreviation of the frequency, and its F indicates the alternating current frequency that measured with hertz, over P. What is the B? B, it's called or indicates into the number of poles. In this we have 2 poles, but in three phases we have 3 poles, north and south. A 2 poles machine equals 2. A 2 poles machine P equals 2. So this explanation of how the 3-phase AC synchronous generator operations works. Thank you, my friends.